Hi YouTube, how are we doing? So today I thought I'd start a little series. I've already posted one video from a prior channel that I worked on, but today I want to talk about how did we get from inches, meters to light years? How did mankind learn the size and scale of the universe? Now, there's honestly other people on YouTube who've done this, but I want to try to take it a little different direction. And I want to sort of go into a little more detail. So, the first part of our story is to describe how did we learn the size of the Earth? You know, it could be something simple, it could be something obvious, but ultimately it was shadows. I'm here sitting, enjoying my little coffee. So, the person who first measured or attempted to calculate the circumference of the Earth was Eratosthenes, Eratosthenes, Greek philosopher, was living in Egypt, and he was a chief librarian of the Library of Alexandria. So it must have been before it was burned down. Now, any of you old enough to remember watching Cosmos? Uh, Carl Sagan actually covers this in one of the first seasons, one of the first episodes of the show. So basically, he lived in Alexandria, and the measurement of the Earth occurred because he knew about the shadows between Alexandria and the modern city of Aswan. So Eratosthenes measured the distance between the city of Alexandria and what was called the city of Syene, Syene, which is the modern city of Aswan. So, so he has these two cities. So what does he do? Well, he knew in Aswan that on the summer solstice, the sun was directly overhead. So if you look down a water well, you would see the sun in reflection. There would be no reflection. There would be actually not no reflection. There would be no shadows cast in the city of Aswan. But in Egypt, he could measure in the city of Alexandria, where he lived, that there was a minimum angle of about 7 degrees. So he hired these professional, hired these professional vematists, Vematists, is people you can hire to calculate the distance between two locations on Earth. I'll gonna try to, if I can figure it out, interject little pictures of little devices they use to help them actually calculate. It's like a cart with some gearing on it to help them keep count. So, what did he learn? Well, let's see. So, in modern times, or using modern measurements, he calculated the distance between Alexandria and Aswan to be about 515 miles. I think the modern air distance is 525. I'll double check when I post this and edit this video. So, given that the Earth's a sphere, they assume the Earth was a perfect sphere. It's not, it's a little ellipsoid. It's fatter around the circumference than the north-south pole due to the centripetal acceleration of mass. So what did he do? He estimated that he took the distance from Egypt, from Alexandria to Aswan, and computed that the meridian has a total distance of 252,000 stadia. The stadia is about 150 meters, 160 meters. So it's estimated. We don't know exactly the true distance of a stadia. It's between 150 and 160. And his answer is within 2% to 0.5%. I'll post a link and a clip of the wiki article. So that's how we get from not knowing the size of the Earth to the size of the Earth. So, cast a shadow, shadow's 7 degrees. He estimated that there are about 50 times the distance to go around, 360 degrees. And it's, if you divide 360 by 7, it's more like 51.3 or something like that. But he used 50 as an estimate, and he still got to within about 2%. So that is how we calculated the size of the Earth. You've had hire someone, figure out the distance between the two cities, and then say, hey, the Earth's round. This is how far 7 degrees is, so that's 360 degrees. So then that takes us to how far are we from the moon? So that's another clip. Now the distance to the moon is a little different. So the distance to the moon actually involves a couple of different techniques, but the one that I think gave the best result, or gave an easy result to attain, is measuring the speed at which the moon crosses the Earth's shadow. So you can say, how big is the shadow across the sky? How many degrees is that shadow? So use the background stars to help you find where the shadow is, right? Based on where the moon intersects. And then you time how long it takes for the moon to cross that shadow, right? They didn't know the Earth actually went around the sun. Well, some people did, but they have no idea how fast the Earth actually moves. So if you calculate how long it takes for the moon to cross Earth's shadow, and you know how big the shadow is against the background sky, so you assume that there's a celestial sphere that goes 360 degrees around for the Earth's orbit, you can compute how far away the moon is based on the Earth's radius. If I can find some calculations, I'll post them. Don't count on it. This is just a very brief intro and talk. I don't want the video to be too technical or to be too long. So from there, you see we have now the distance to the moon. So that's a little easy. So then you need to know the relationship to the distance of the planets. Well, Mercury and Venus are pretty easy. I just realized I was on the wrong mic. So hopefully this part gets a little better. I don't want to have to try to repeat the first half, but it's only about 7 or 8 minutes so far. So let's continue. Where were we? So we needed to now figure out the size of the solar system. And that's a little easier, not by much. Actually, the inner planets were easy. The outer planets were extremely difficult. And that's because the inner planets never deviated far from the sun. So they knew that inner planets had to be within the Earth's orbit, assuming you accepted the Copernican model of the solar system. And because the planets never deviate far from the sun, if you do a little geometry and you draw tangents, so the maximum deflection would be the tangent to a circle that's the circumference of each planetary orbit. And if you assume the sun-Earth distance to be 1, and you take the angle, the sine of that angle, is it? Yeah, the sine of the angle will give you the distance from the sun to the planet. So you get Mercury and you get Venus. So, yeah. So that was Mercury and Venus. That's very easy. Mars, which is, I discuss on the other clip that I have, Mars actually took the work of 2 people. It was pretty much determined by Johannes Kepler, but he had to kind of like steal the data from Tycho Brahe. So Kepler worked for Tycho Brahe and did some observations for him. And upon his death, I believe he thought he was entitled to the data. So upon Brahe's death, he kind of like stole the data. And it was a lot of data. I mean, it's like they say, everything, data is everything. Data is money, data is gold. So what did Kepler do? So Kepler did some geometric calculations of Mars's orbit. So I think Mars's year is like 444 days. I'll put an overlay if I'm incorrect. So in the video that I posted prior, I'll leave a link, you can calculate not only the distance, I believe, but he figured out the distance another way. So let's talk about that first. Let's not deviate. So let's say you wanted to calculate the distance from Earth to Mars. Well, you know how long Earth takes to go across the sky, and you know how long Mars takes to orbit, right? So Earth traverses, the way you do Earth is you find out where the sun is against the background sky. And it takes the sun about 365 days to return to the same spot in the background sky. So you know how fast the Earth traverses the sky. It's 365 days, it's 360 degrees, so it's about 1 degree a day. So then you look at it and say, hey, we know how long it takes Mars to go across the sky. You know, how long does it take Mars to return to the same spot in background sky? So then you're like, okay, we can use this. And how do we use this? So how do you do this? So you wait for a period in Mars's orbit where it goes retrograde. And when it goes retrograde, when it enters retrograde, you can determine how long it takes for Mars to return to the same spot against the background sky, right? So you find Mars, find a sky, you find a star, you wait for it to go into retrograde, And then you determine how many days it takes for Mars to return. And you say, well, Earth moved so many degrees across the sky. So I'll try to put a little graphic overlay. So you have two parallel lines. One is Earth and Mars and a background star on day one. And then there's another parallel line, Earth, Mars, and a same background sky, but with the Earth and Mars further along in their orbit. So you do a little geometry. Sun to the Earth is 1. You have an angle. You do some trig, and then you can determine the Earth-Mars distance, and then knowing Earth-Mars, you know what the Sun-Mars distance is with respect to the Earth. So right now, everything is based on the orbit of the Earth, the radius of the Sun-Earth distance, which will eventually be called one astronomical unit. So what do we do from there? Now you're like, okay, so Kepler got the distance, but he needs to get the shapes of the orbits. And what you do is you take a day and you find out where Mars is in the sky. And you know how many days a Mars year is. So you say, okay, where's the Earth, Sun, and Mars relationship that many days later? So you look up in your tables and you say, well, the sun is in this part of the sky, which would put the Earth in this part of the orbit. And then you do it a couple of more times. And then you have like 4, 5, 6 data points. And then you look at another day, maybe 1, 2 days later. I want to point out that 3 blue, 1 brown, I think. Yeah. I had a great video on this, and I'll leave a link to it. But so if you do it again, you get a bunch of other data points. And if you keep doing it, you get a bunch of other data points. And if you pick enough days to plot out where Mars is, you can pretty much determine the shape of the Earth's orbit. And then how many days it take for it to go from one point to another point. So that's basically how Kepler got his other laws. Planets orbit from a point on an ellipse, and they cover equal areas in equal times, meaning they speed up when they're closer to the sun and they slow down when they're further away. And he got the relationship of the orbits. If I remember correctly, it's radius cubed is proportional to period square. So I know Jupiter is about 5 AU, and it's 125 is 5 cubed. And then you take the square root and it comes out to like 14 or 13 or some crazy number like that. So yeah. So now we have the size of the solar system in relationship to the Earth's sun distance. So we know the ratios of the distances. We don't know the exact distance. And the exact distance actually comes down to the transit of Venus. Everyone, well, if you're a science person, you probably know this one, but it comes down to the transit of Venus. expeditions were sent all over the planet to measure how long it takes for Venus to traverse the sun. They assume a certain angular distance, so all of the measurements were done in angles. So the sun is about 1 degree across the sky, and you time how long it takes Venus to cross the surface of the sun. And they took different measurements. When it entered, when it first touched the corona, the front side, when the back side of Venus touches the corona, touches the surface, the edge of the sun, and then 2 more data points at the end. And these were all timed. Now, why did they have to measure the time it takes Venus to traverse the sun? Because they needed to measure the chord length. And if you know the chord length of a circle, and you do some trigonometry, you do some geometric calculations, you can determine the distance from the chord to the center of the circle, right? So the longest chord, the diameter, goes through the center. And as you move away from the surface, you move away from the center, you get distance from the center related to the chord length. But, I'm just babbling a little bit. Forgive me. So if you know the chord length of different observation points, okay, you get parallax. You get a parallax shift from different observers. So a northern hemisphere observer will see Venus below a southern observer. So you draw a line, you have the person at, let's say, the North Pole sees Venus, and from his perspective, Venus is below the center of the sun. And if you're on the southern hemisphere, if you're in the South Pole, and you look at Venus against the sun, you're going to see the sun above the center. Let's say it's extremely exaggerated, but it's something like that, right? It's not going to be exactly above, but one's going to be above, one's going to be below. That's the important part. And if you measure the chord lengths, because you can't really measure the distance Venus is from the center of the sun. That's almost impossible to measure with the instruments at the time. So if you measure different chord lengths, you have 2 different measurements for the distance to the center. If you have 2 different measurements for the distance to the center, then you know what the difference is between the 2 chord lengths, right? So if one chord length is 1 and one chord length is 0.7, then the distance between the 2 chords is 0.3, as a mathematical example. So once you have that, you now have the angle that you need, the parallax angle. Okay, once you have that, you have the distances of all the observers, and you can triangulate the distance to Venus in terms of the proportion to the Earth distance, okay? And you have the distance in a unit you can measure, which is miles, right? So you have 2 points on a sphere. It's easy to find the distance between 2 points in a sphere, okay? And you have your parallax angle, which is the angle, it's the angle made from observer to Venus back to observer. So observer A, Venus, observer B. So it's that angle. So we call it O1 V O2. Okay? Once we got that, we discovered that Venus is about 0.7 of the distance from the Earth to the sun. And converting it into miles, we discovered that the Sun-Earth distance is about, on average, 93 million miles. And knowing that the Earth-Sun distance is 93 million miles, we now have a measure for the circumference of the Earth's orbit and its diameter. And once you have the diameter, it's 186 million miles, right? 93 times 2. You can now apply parallax triangulation against background nearby stars. And that's going to be in the next section. Bye now. Hi, and welcome back. So today we're going to continue with the scale of the universe and how we got to measure things the way we discovered them. So in the last episode, we left off with the Earth position in the solar system, the distance from the sun being determined from the transit of Venus. And the Earth's diameter was measured to be 186,000 miles, 186 million miles. It's 93 million miles from the sun on average. So once you have that, you can use that and the same technique to measure the distance to Venus to measure distances to the nearby stars, up to, I believe, a couple of hundred light years. So, given that, astronomers began measuring distances to the local stellar neighborhood. And some of the stars that they measured were Cepheid variables. It's a variable star. Its name is derived from Delta Cephei, one of the first variables to be discovered in this class, thus its name. In the Cepheus constellation, other stars that you might know is Polaris is a Cepheid variable. And one of the brightest Cepheid variables is RS Puppis. Why are we bringing up Cepheid variables? Well, this is where the story gets interesting. You see, back in the early 1900s, there were female astronomers in Harvard University. The men did the observations and the women did the calculations. And one of these women was Henrietta Swan Leavitt. Okay, this is important. She began measuring Cepheid variables, or what were believed to be Cepheid variables, in large and small Magellanic clouds. I believe it was mostly the large Magellanic Cloud, but I think she did measurements on the small Magellanic Clouds. And what she discovered is, and here's the trick, she assumed that the stars in the large and the small Magellanic Cloud, because they're in a group, were approximately the same distance to the Earth. So she can take out an unknown variable, meaning distance. So any observations she made could be used and not have to worry about distances. It's a little convoluted. So Henrietta Swan Leavitt made observations of the small and large Magellanic Cloud. And one of the observations she made was that the period of Cepheid variables in the large and the small Magellanic Cloud had a linear relationship when using a log scale believed for parent brightness, that
there was a linear relationship between the brightness and its period, between when it's peaked and when it's dim. Okay? And with this, she was able to determine that the Large Magellanic Clouds were an X unit further away than her reference star. I believe it was Delta Cephei. I think she determined that the Large Magellanic Cloud was 100 times farther than Delta Cephei. If it's wrong, I'll put a correction in the video. So, how is this important? She was able to now utilize a standard candle, as it's called, to distances to distant stellar objects. It's very hard to know how bright something really is if you don't know how far away it is. But it's really easy to measure how fast something goes dim and dark, dim and dark. Sorry. Light and dark, light and dark. Okay, these are all unscripted. Please forgive me. These videos will get better hopefully with time. But the big takeaway is she published this and they now have a standard candle to the outer universe. Right? So we went from knowing the ratios of the solar orbits of all the planets, using parallax and the transit of Venus to determine the distance of Venus. And then from determining the distance to Venus, you can determine the distance to the sun, right? Because you know that your distance to Venus is a small fraction. I think it's Earth to Venus was 23% of the total distance to the sun. So if you know 23% of the way to the sun, it's really easy to get 100% the way to the sun. So we go from there. We go from knowing the size of the Earth's orbit to using parallax to knowing distances to stars. Some of those stars were Cepheid variables. Those Cepheid variables then gave us a distance marker to the small and large Magellanic Clouds. Right? Because you can assume all the stars in the Large Magellanic Cloud are the same distance to the Earth. So you can develop that relationship. What made the Cepheid variables so special, so important? Well, it comes down to that they operate on what's called the K mechanism or the kappa mechanism. And this is from Wiki. So it says the cycle is driven by the fact doubly ionized helium, the form adopted at high temperatures, is more opaque than singularly ionized helium. Normally, when you compress a gas in a star, it becomes ionized, and that ionization allows photons a freer transport out of the star. They're not blocked by any electrons capturing them and re-radiating them in different directions. So the doubly ionized helium actually gets more opaque, less transparent as it's compressed. That actually causes the helium to absorb energy, gets warm, right? If you're not letting photons through and you're absorbing them, you're absorbing energy. So where does that take us? So you have a star and its doubly ionized helium is compressing, becomes opaque, dims the star, the gas warms up, expands, becomes less opaque, more transparent, lets more light through, cools off, and then pulses again. So in a normal star, it doesn't pulse. It'll compress till a certain transparency is achieved. And that's the light that shines through the atmosphere, the gases. All right. So now we have a distance marker that we can use by measuring a period. And then measuring a distance. So you get the apparent brightness, and then you get the absolute brightness. And I think the absolute brightness, its intrinsic brightness, is how bright the object would be if it was 10 parsecs from Earth. Okay? This eventually leads Edwin Hubble. So this eventually led to not Halley, he's the comet guy, Edwin Hubble. Okay? So Edwin Hubble in 1929 discovered the distance to the Andromeda Nebula by finding a Cepheid variable, measured its period, and determined its distance. And the distance he got was on the order of 2 million light years. This object was definitely outside the bounds of the known galaxy at the time. So now we have a distance marker, and using these Cepheid variables, Hubble, with Hubble's law, was able to find a relationship between the distance of a stellar object and its redshift. Hubble's law, you probably know it as Hubble's constant. And now we have a way of measuring distances all the way out to the far reaches of the galaxy. In the next segment, we'll talk about type 1a supernovas and the mechanism at which they became the next standard candle, and the ramifications of the comparison between the Hubble constant and the type 1a supernova data in the next part. Hi, YouTube. So I want to get back to the scale of the universe. So last time we left off, we talked about how we got to measure the distance to the Andromeda galaxy. We were able to use Cepheid variables as a standard candle, and that allowed us to measure the distance to nearby Cepheids. Polaris is a Cepheid variable. Cepheid is a Cepheid variable. It's the star that the class of stars are named after. I think it's called Cepheid. And with that, we can get the Hubble constant, and Hubble discovered that the farther things away are, the greater the redshift. So he can use the redshift to extrapolate distance, and he found out that galaxies were actually external to galaxies. Andromeda used to be called the Andromeda Nebula, then it became the Andromeda Galaxy. After it was discovered, it's outside the known galaxy. But then you want to have a kind of different marker. You want to have a marker that's independent of the redshift. So that's where type 1a supernovas come from. So type 1a supernovas are white dwarfs, accrete matter. They accrete matter to the point where the material on the surface undergoes a runaway nuclear reaction, and the star basically explodes, blows itself apart. So those all happen at the same level. So regardless of the size of the neutron, is it the white dwarf or neutron? Hold on a second. Hi, I'm back. Yes, it is white dwarfs. The limit is the Chandrasekhar limit. And regardless of the initial mass of the white dwarf, if enough material accretes on the surface and hits this limit, boom, you get a type 1a supernova. You can treat those as standard candle. Where does that take us? So back in 1998, there was a supernova, type 1a supernova research that was conducted, and they then plotted the type 1a supernova data against solar redshifts for those objects. And it was a very unusual, it was a very unexpected discovery where the objects, if you plot them out, so within 1 billion light years of Earth, the plot for redshift, the plot for luminosity of apparent luminosity of type 1a supernovas, meaning the light that actually you measure, I believe, on Earth, compared to redshift, is linear. And then they diverge. So if it diverges one way, it's an accelerating universe. If it diverges the other way, it's a decelerating universe. Everyone expected it was going to be decelerating, and I guess they wanted to measure how fast it was decelerating. Well, we know that it's accelerating, and they actually won a Nobel Prize for that discovery. So that takes us pretty much to the end. That's the type 1a supernova. I'll include references to the graphs that mention that it goes one way or another. And that takes us, I guess, to the end. This segment was not going to be very long. The type 1a supernova data is very well understood now. It led to the theory or the hypothesis of dark matter, and that dark matter is accelerating. There's dark energy. Actually, dark matter is the phantom sort of extra mass that's in the universe. The dark energy is being used to explain why the universe is accelerating rather than decelerating due to gravity. So that's it. I'm going to paste this together with the other videos, and I hope some of you like it. It's not usually what the YouTube algorithms are expecting, but I'm trying something, you know. I do have a full-time job, so hopefully I can engage enough of you and I can get comments and we can see what everyone else is interested in learning about. All right, thank you and see you next time.